All right, so today we're going to be finishing up chapter 13. Going to look at section 13.4. If you remember, what we've been really working on in this chapter has been mainly focused on this idea of solving or factoring polynomials. So, oh my God, come on, just like let it go. All right. So remember we drew out this factoring diagram, and we noticed that there was like some blank spots in here where if we couldn't, or if our polynomial wasn't in the quadratic form, there's really nothing else to do. Or if our four-term polynomial wasn't factorable by grouping, there was nothing to do. Or if we had 5 or more terms, we didn't have anything that we were going to do. Now, in sections 13.3, we started to expand on what we could do by adding in this idea of using polynomial division to help us do that factoring. So let's just go back and recall a example from 13.3 as just like a starting off point. So here we have the polynomial f of x equals 6x cubed plus 23x squared minus 83x minus 30. Now this would be one of these degree 4 polynomials, but it isn't going to be factorable by grouping. So it would have landed here on our factoring diagram, but we can now continue on. So what we wanted to do is we started by identifying our possible rational zeros, which are going to be the factors of the constant term divided by the factors of the leading coefficient. So we have our factors of 30.
Dr. Phil, have you taken a test?
No.
Can I see Claire?
Yes.
Thank you.
Sure. Over the factors of the leading coefficient, so our factors of 6. So if there's a rational zero, it has to come from the values on this list. Now, if we knew which ones that was going to be, we could use some polynomial division to figure that out and start factoring this polynomial. Unfortunately, with the list the way it's written right now, there's just like too many to just want to guess blindly. So let's start by just graphing this and looking at the picture and seeing if that can inform a choice of starting points. So I just type this into my calculator and I'm just going to hit graph. Oops. Well, I'd be like going back to the standard window and hitting graph anyways. Oops, I didn't do that. So let's do a zoom standard. Okay, so if I look, it looks like I have an answer here at -6, something between -1 and 0, and another answer between 2 and 3. Do you guys see the x-intercepts here? Okay. And I'll write it this way. Now, when I look at each one of these x-intercepts on the graph, looks like the graph is just kind of passing straight through each of these. What that's going to tell me is that each of these should have multiplicity 1 and really only be used one time in building out my factored form. So if I look at this, x equals -6 looked pretty, like on the tick mark. I'm pretty confident about that. But this value between -1 and 0, well, there was like a lot of choices there on what that could have been. Right? Like all of those things could be plausible. Similarly, between 2 and 3, well, what could that have been? It could be like, like 15/6 is in there, and like 5/2 are both between that. I don't know if there's another one, but we're not sure. So any possible 0 from there that we picked would still be kind of a guess. I'm not really into guessing. I'm just going to choose this one to be my starting spot. So I'm going to set up my synthetic division here. And let's go ahead and execute that. And that's good. I got the 0 there for my remainder at the end. So what this is telling me is that my polynomial factors to x plus 6 times x squared minus 13x minus 5. The x plus 6 came because I got a 0 reminder when I divided by, or did my polynomial or synthetic division with -6. And the 6x cubed or squared minus 13x minus 5 is coming from the quotient of that division. So if I want to continue moving forward, I'm going to need to either factor solve this remaining polynomial here. So since it's quadratic, it should factor via the factoring tree. So I can do that long factoring process on it because its leading coefficient isn't 1. So I'd be looking for two numbers that multiply to give me the leading coefficient times the constant term, that's -30, and add to give me the middle term, that's -13. Those two numbers are going to be -15 and +2. What those numbers allow me to do then is it tells me how to divide up that, or break apart, I should say, that -13x. So I'm going to break it apart into -15x plus 2x. Now that this is in 4 terms, I can try to factor this by grouping. From the first group, I can take out a 3x, leave me with a 2x minus 5. In the second term, or the second group, I should say, there is the only factor in common between 2x and -5 is just 1. So if I look from the first term, I have a 2x minus 5. In the second term, I have a 2x minus 5. So if I factor those out, I'd have 2x minus 5 times the 3x plus 1. So that's going to give me then my fully factored form for my polynomial. If the directions asked to factor it, I would be done at that point. If it's asking for a solutions, though, I would just set that polynomial equal to 0. And then I can set each piece equal to 0 and solve them each individually to get -6. Well, we knew that already. I add 5 and divide by 2. So it was 5 over 2. And then subtract 1 and divide by 3. Oh, it was -1/3, so I see that, yes, indeed, that looks like it supports what I saw in the graph. So that's where we had gotten to previously, is we'd been able to extend that factoring diagram that we built at the beginning to deal with some of these situations. What I want to do now is just kind of continue building out this process that we've already started, to give us a little bit more information, allow us to do this a little bit more optimally. So new here today, we're going to give you guys 3 more theorems. So the first new theorem is called the fundamental theorem of algebra. And what the fundamental theorem of algebra says is that every polynomial equation is solvable. And in fact, even better than that, it has the number of solutions to that polynomial equation are going to be equal to the degree of the polynomial, provided that you're counting any multiple solutions. So if your solution has a multiplicity of 2, it counts as 2 solutions. And that you're counting all the imaginary solutions as well. Okay, so all that is saying then is that, okay, I can count, I'm always going to have n solutions, where n is the degree, provided that I'm counting all the duplicates and imaginaries and all that jazz in between. Sound good? Yeah, okay, but whatever, Mr. Kulik. The other 2 theorems we're going to have, one is called the irrational conjugates theorem. And the other is the complex conjugates theorem. So the rational conjugates theorem says that if a polynomial with rational coefficients has the 0 a plus square root b, then it also has the 0 a minus square root b, as long as b is not like a perfect square. Because if b is a perfect square, then a plus b is not a irrational number, right? The complex conjugates theorem says almost the same thing. Except instead of saying just do this the sneaky way. And then I want to update rational to be real. And this should be a plus bi and a minus bi. And then I don't need that. Well, I guess I should say b is non-zero. Right? Because if b isn't 0, then that's not an imaginary solution. Check. Yeah, go ahead. So, for example, if I have a polynomial with rational coefficients, and I have like 1 minus square root 2 is a 0, then I also have to have 1 plus square root 2 as a 0. Or if I have a polynomial that has square root 7 as a 0, then it also has to have like negative square root 7 as a 0, right? Or if I have a polynomial with real coefficients that has like 1 minus 3i as a 0, then it also has to have 2 plus 3i as a 0. Or if it has I as a 0, or I should say negative I as a 0, then it also has to have positive I as a 0, right? Where you're always going to get these guys coming in conjugate pairs. So in your homework, what you'll be asked to do is you'll say, okay, like write a polynomial with real coefficients, minimum degree with the zeros, say 1, negative 3, and 1 plus I root 2. So we'd already kind of done some problems like this earlier. So just like we had before, we'll start by identifying that each of these zeros has to be a solution. But because I need to have real coefficients, and I have this I, or 1 plus I root 2, I'm also going to need an additional solution of 1 minus I root 2. I need to have its conjugate pair with it. And then just like we did before, we'll start by getting these things equal to 0. So subtract 1, add 3, subtract 1 plus I root 2, and then subtract 1 minus I root 2. So I have these four polynomials now, and if I multiply all these polynomials together, since each of these 4 polynomials is equal to 0, the product of these will also be equal to 0. And all I need to do now is to FOIL these things out together. So I'm going to FOIL these 2 together to start, and then FOIL those 2 together, and then FOIL the resulting things together. So this first pair that it's in green, I'm going to just FOIL quickly in my head. I get that. The second pair, I'm going to go a little bit more carefully and kind of just show you what I'm doing. So I'm going to treat these things in parentheses as just like a one big thing. So when I do my first and my outer, I get that. When I do my inner and my lasts, I get that. Is everybody okay so far? I'm then going to, I should have probably written it. I'm going to put those X's in the front. It'll make a little bit more, make the arithmetic a little bit easier if I do that. Now I'm going to distribute these through. When I do that, though, I got to remember to take my negative sign with me. And then this thing I'm going to also FOIL out, but I notice that that is just like a difference of 2 squares, right? All right, so what do we got here? Everybody okay there with my foiling? Just multiplying things out. Now if I look here, I have an I root 2 times x and a negative I root 2 times x. Those guys are just going to cancel each other out. And then I have this I root 2 squared, so that's going to be I squared and then root 2 squared. Who remembers what I squared is equal to? Close, -1, and root 2 squared is just 2, right? So that's just going to be like a +2 at the end. So I have a subtraction symbol, and then -1 times 2 just turns into +2, right? All right, so if I collect everything together in that second set of parentheses, I have my x squared, I have 1x, and then another x, that's -2x, and then a +1 and a +2, that's +3. And now I'm going to FOIL this out. And now if we combine our like terms, I have just the x to the 4th. I have a -2x cubed and a +2x cubed. Those cancel out. I have a 3x squared, a -4x squared, and a +3x squared. That's just going to leave me with the -4x squared. And I have a 6x and a 6x. That's going to be a 12x. And then just the -9. So there's my polynomial that I'm looking for. Woof! What was the worst part? Foiling it out, right? Getting the polynomial in a factored form, not too bad. But woof, foiling that thing out was a lot of bacon there. All right. The other thing that we're going to be doing now is going to be asking you still to solve or find the zeros for polynomials. But this time we're going to ask for all the zeros for the polynomial. What that means is that we'll also have to find any imaginary solutions. I want to point out to you that these imaginary solutions you cannot get them from your calculator. So just like graphing and finding the x-intercepts, well, you'll never find the imaginary solution, so you have to be able to do it with the synthetic division. All right, so just to kind of restart our process, fundamental theorem of algebra tells me that I should have 3 solutions to this. I look for my possible rational zeros. That's going to be the factors of the constant term divided by the factors of the leading coefficient. So my factors of 36, there's a whole mess of them. and then over plus or minus 1. But I don't have to write over 1, right? Everybody's good with me not doing that. If I type this in and I look at my graph, let's look what I see here. See if we can find a good starting spot. So I see one solution here at -4. And I noticed that was a straight, right? So that's just going to count as one solution. But I am looking for 3. Where are the other 2 solutions going to be? They're going to be imaginary. So we're going to have to find those algebraically. I'm not going to be able to get those off of the calculator. Even if I graph and use the 0 command, it will not find those ones. All right, well, let's start doing our synthetic division. So I got the 0 that I was hoping for. So what this tells me is that my polynomial factors to x minus 4, because I got a remainder 0 when I use -4, times x squared plus 0x plus 9. So remember, those numbers at the bottom of our division are the remainder, the constant term, the x term, the x squared term, and so on and so forth. Always reading from right to left. It's the only time in mathematics where we're going to read from right to left. Now, if I look at the x squared plus 9, I notice that that's not factorable. So if I want to find my solutions, again, I can just set each of these chunks equal to 0. So -4, well, I kind of knew that already from looking at the graph. To solve x squared plus 9 equal to 0, I can either use the quadratic formula, or because there's no regular x term, I can just solve this directly. That's what I'm going to choose to do because it's a little bit simpler. So I subtract 9 from both sides. I square root both sides. That gives me plus or minus. The square cancels the square root. When I square root a negative, what do I get? I get an I, and the square root of 9 is just 3. So I have plus or minus 3i. So I have one solution here at -4, a second solution for positive 3i, and a third solution for negative 3i. There's my 3 solutions that I was looking for. Mm-hmm. Let's do that again. Okay, so again, start with the fundamental theorem of algebra. Because it's a degree 4, it tells me I have 4 solutions. My possible rational zeros are going to be the factors of the constant term divided by the factors of the leading coefficient. Okay. And then I'm going to go to my graph and take a look and see what I can see from looking at that. Oops. It's supposed to be 4. Okay, I hit graph. And oh, rats, it doesn't look like either one of these are falling necessarily in the range that I was looking for. And that's probably because I forgot to type in the 62x. So let me just retype that again real quick. Whoopsie-daisies. Yeah, still doesn't look great. So I'm going to zoom in a little bit closer to what's going on here. Looks like everything, all my x-intercepts are happening between -2 and +1. So I'm just going to change my window to reflect that. So if I look at this x-intercept, that one looks like 1/2, right? Pretty positive that's what that's got to be. Everybody agree? This one over here is a little less than -1, but not quite -2. If I look at that, that looks like it's got to be like -5/4. I think is the only thing that's going to be close to that. And again, I notice both of those are just kind of passing straight through. So I know I should be looking for two imaginary solutions here. Now, unfortunately, I'm stuck with fractions each of these times, yuckarooskies, but it is what it is. Given the two fractions to start with, though, I'm definitely picking 1/2 over -5/4, right? Like, so I'll go ahead and do my synthetic division. So again, that worked, yay. So my factored form is x minus 1/2 times 8x cubed minus 22x squared plus 16x plus 70. Now, unfortunately, if I look at this, that's 4 terms still. If I take a quick look, I'm going to be pretty convinced pretty quickly that that's not factorable by grouping. So I'm going to need to continue doing synthetic division here. So the -5/4 is what we're going to have to do. Yuck! All right, let's see. That's -10. And that's going to be 40. Oops, yeah. 56. And that's going to be 14. So that's -70. Oh, good. So that worked. So I have still the x minus 1/2. And I have an x minus 5/4. And then I'm going to have this guy here. Yes, sure. Now, if I look at that leftover piece, that's quadratic, so there's a chance I could factor that, or if not, use the quadratic formula on it. If I look, though, the leading the coefficients for each of those, I see there's a greatest common factor of 8. I'm going to take that 8 out. Yeah.
Why did you change it from 1/2 to minus and then -5?
Because that's how we always change it. Like the sign here is always the opposite of over here. Because remember when you take like the factor x minus 1/2 is the solution x equals 1/2. So you're plugging this in to here, and when it gives you a 0 out, you write the factor like that. Does that feel okay?
I think I had it mixed up.
Yeah. All right, so if I wanted to give this in a factored form, This 8 I would probably think about as like 2 times 4. I'd multiply the 2 into that parenthesis and the 4 into that parenthesis. And that'll give me like things looking pretty. Now if I try to factor x squared minus 4x plus 7, are there two numbers that multiply to give me 7 and add to give me negative 4?
No.
Not real ones. So what am I going to do if I want to solve this thing? Can't use factoring to solve it. I'm going not use my calculator either. I'm going to use the quadratic formula. Yeah. So that's negative b plus or minus square root b squared minus 4ac all over 2a so that's 16 minus 28, so that's a negative 12. Negative 12 is, or 12 is 4 times 3, right? So plus or minus. The square root of 4 is 2. Because we're doing a negative, I get an I. And then I still have that square root of 3 left over. And then to reduce this a little bit more, if I think about this all with a common denominator of 2, I can reduce this down to just be 2 plus or minus I root 3. So I have 1, 2, and then 3 and 4 solutions. Again, we have 2 solutions there because there's plus and 1 for minus. So 2 plus I root 3 and 2 minus I root 3. So that's counting as 2 answers. And that's kind of the gist of it. Like, this is as good as we're going to get for this kind of a class. When you do like your math degree and go to grad school for mathematics, you can take a whole course called computational algebra, which is just devoted to like techniques on solving polynomials. Yeah, and go to grad school. Yeah. Notice it's not if, it's when. So that's going to wrap up chapter 13. So you should be able to finish the problem set 36 through 53. Next time in class will be the review day. We'll make our half sheets and whatnots. And then the plan is Friday is the test day. So if polynomial division is a problem for you, Francis, try to find some time this week to come pay a visit and get a little second lesson on how to do that. Because there's not much you'll be able to do on this if you can't do polynomial division. Oh, good. Well, make sure that you ask Miss Morgan to like walk you through that again. Okay. And the other thing with the, notice that this process that we're doing here, this is rather lengthy, right? I can't ask you to do this very often on a test. And even if I did, if you do this and you make like one little oopsie somewhere in there, it can be like, have a lot of stuff wrong. I'm going to do my best to write test questions where it's like, you know, I've done part of it for you and ask you to just do the next step so that it's not reliant on your previous work or asking you to do the entire problem over and over and over again, because it takes too much time, and there's the chance that if you did something wrong along the way, you get answers that don't make any sense, and then it's really confusing. So I'm going to do my best to write the test questions in a way that, will you have to do this process all together? Yes, but not over and over and over again. I'll also ask you to like find the possible rational zeros for this polynomial, and then like how many solutions can this polynomial have, and like, you know, like ask you to do the different parts of this process without having to do the whole thing over again. where each one of them is like its own separate problem, not relying on the problem before it, so that if there is a mistake, it doesn't carry through and just like a bunch of stuff becomes wrong because you forgot a negative sign or like you multiplied something wrong or whatever. You know what I mean, guys? So that's it for me.